go farther from the nucleus, as you get to see that they are not reactive. They are not actually very much dependent that they need to react with a molecule and complete their octet and become equivalent to the charge of the nucleus. Fine, the nuclear and the, you can say octet charge should get completed, or the octet should get complete. So they become less reactive as the size increases. Fine, you can actually understand by the concept that you tend to find all those thin people are more active according to the social, or you can say the mental state, that you find that as the size actually increases, people tend to become less active. They are very lethargic. They are not very active enough. So is with the, you can say, periodic table also in halogen family. As the size increases, you go down the group, activity or reactivity decreases. So in a group, the most reactive element is going to be the topmost one, the one which comes the first. So fluorine is the most reactive among all. Next slide, please. Now, let's come up with some of the questions. Because of no animation coming up, answer is still marked here. So let's see, how many electrons do the halogens have in their outer shell? It's 5 outer shell, because 2 in S and thereafter 5 in P. So outer shell is the P, so it will be 5. Fine. Next slide. You don't need to mark 7. Please, previous slide, please. Many times, what happens? Students make a mistake and they mark 7. 7 is the valency, does not mean, because you have to be very precise in your JEE exams that what has been asked. Halogens have in their outer shell. S is not the outer shell. The outermost shell comes up as P. So you need to mark 5. Both the options are given. Many of the students may be marking 7, but that is an incorrect answer, because 7 is not the outer shell. P is a subshell, but they are asking about outer shell, no? That's true, but subshell and shell is taken up as same. But it is not taken as the valency. If it would had been asked as valency, then it had been a 7. Fine. Next slide, please. How many atoms exist in halogen molecules? How many atoms exist in halogen molecules? This answer is not marked correctly. It should be 2. Fine, because they can form covalent bond in a molecule, and there can be Cl2, Br2, all those kinds of elements. Next slide. What is the order of increasing reactivity of the halogens? This is also marked, it has to be marked here at the option B, because you know as we go down the group, the reactivity decreases. The smaller the size, more active, or you can say more reactive molecule is going to be. Fine, next slide. Here we see the chemical properties. The reactivity is most for fluorine, thereafter chlorine, bromine and iodine. React by gaining electrons. Fine. That is why I told you they have a very good oxidizing power. Oxidizing power, oxidizing agent. Because they reduce themselves and oxidizes other. At the expense of it only it happens. Because of which, the oxidizing power would be at the same level as the reactivity goes. If we say which one is the most oxidizing agent, the better oxidizing agent would be the most reactive among the all, because they all are oxidizing agent. Fine. Halogens, all the halogens are good oxidizing agents. Fluorine molecule, chlorine molecule, bromine, iodine, all the molecules are oxidizing agents. But if we need to rank them, then their ranking comes up as their reactivity comes up. The more the reactive, more the oxidizing agent. Fine. So the oxidizing power or the oxidizing agent actually comes up as fluorine as the maximum and iodine as the least. Fine, because of its reactivity series. Clear? Next slide. Now, reaction with sodium. As the reactivity goes, fluorine will actually react readily, or you can say the violently of the all, and iodine will react the least among the group with sodium. Though sodium is very favorable to be reacted, because sodium has 1 extra electron and halogens have 1 less electron. So that kind of interaction is very favorable to form an ionic bond and have a full octet for both of them. Fine. But among the group, you will get to see that fluorine reacts the most and iodine the least. Though all will react to complete their octet, But comparative study will show that fluorine is the most reactive and least is the iodine. Next. Now reactions with hydrogen. Same as you get to see with the hydrogen also, fluorine reacts most explosively. Explosively means very fast and very, you can say preferably, fine. And iodine reacts slowly and reversibly even on heating. You need to provide some energy to actually let it get reacted with the hydrogen, right? So the reactivity goes down as we go down the next. Reaction with phosphorus also you get to see, like fluorine molecule is the strongest oxidizing agent. If something is a good oxidizing agent, that means it will oxidize the other molecule or the compound it is reacting with to the maximum of the oxidation state. It will oxidize completely. Now phosphorus has oxidation state as +3 and +5. We all know that very well. In nitrogen family we have studied this. So it will get completely, or you can say the maximum oxidation will happen with the very good oxidizing agent, and it will go to the maximum oxidation state with the best of the oxidizing agent. Since fluorine is the strongest oxidizing agent among the whole of the group, it is going to the maximum oxidation state, that is PF5. Fine. And as we go down the group, it goes to the lower oxidation states. It won't form PI5 with iodine because it is an oxidizing agent. It will oxidize phosphorus, but not to that great extent as fluorine will. Fine. The extent will different. It will readily oxidize with iodine as well, but the extent will be less. So because of which it will go to the lower oxidizing state. Next slide, please. Yeah, here you can see that bromine and iodine are not strong oxidizing enough, so it is not going to the highest possible oxidation state. Next slide. Reactions with xenon and carbon. Xenon and carbon, you get to see that fluorine reacts directly with all non-metals except nitrogen, helium, neon and argon. They do not actually react readily with them, but it will even react with diamond and xenon on heating. Fluorine is so reactive that actually we will talk about xenon in detail when we will talk about the noble gases. Actually, xenon is a noble gas, but it comes down the group. So here what happens, the trend goes differently, that because noble gases are not reactive at all, so the you can say being inert, as we go down the group, goes down. So it starts reacting somewhere or the other. Fine. So carbon and fluorine also gets reaction, that means with the diamond, and with xenon also it forms multiple oxidation states and gets you different compounds. Fine. Next slide, please. Reaction with xenon. Xenon can expand its octet by utilizing vacant it has d orbitals in between. So what happens, though it's a noble gas, an inert element, but because it is very far off from the nucleus size, or you can say the size is very big, so being inert also reduces. Whatever property is there will reduce as we go down the group. So halogens being reactive molecules, it reduces reactivity, reduces down the group. And noble gases being inert, the inertness reduces down the group. Fine. So xenon comes very down the group. So the you can say inertness actually reduces to an extent, and you can see that xenon has vacant d orbitals. So this is the complete octet for xenon, and this is for fluorine. 1 electron is less for fluorine. Octet is complete for xenon, being inert gas. Fine. What happens if we provide some energy to that? 1 electron can go to this of the 5d, next slide, and it can accommodate 2 fluorine molecules with it. Another variable oxidation state, if further energy is provided, 1 more electron from this side will go to D. And now 4 fluorine molecules can accommodate with them. Fine, because fluorine is only 1 electron. So sharing of 4 fluorine molecules can take place and forming XeF4. Fine, next slide please. Or you can say here 1 more electron is being expanded to this side. It can accommodate 1, 2, 3, 4, 5, 6. So 6 fluorine molecules can be, 6 fluorine atoms can be accommodated, forming XeF6. Next slide, please. And reaction with xenon actually can happen only because gap between NP and ND subshell goes down the group. Like that as I told you, that whatever is the main or dominant phenomena of that very group, as we go down the group because of this increase in size, that very property decreases. Fine. So the promotion of electron from NP subshell to ND subshell becomes easier down the group because nucleus does not have that good effect or impact on the outermost shell as we go down the group. So now they can move out here or in wherever. If you say that nucleus is a kind of a teacher or a principal, as farther the class or the subshell goes, the impact or the effect of nucleus reduces. Fine. So because of which, if they were inert because the octet was complete, now they are free to move and become reactive. If they were reactive, they can be lazy and they may not react. If they are farther from the, you can say, the main authority or the principal or whatever, whosoever is actually judging them all. Fine. Understanding this very aspect, you will get to know the concept. Next slide, please. So it goes like this for xenon, and we can have XeF6 kind of a structure. Energy released by forming more single bonds overweighs the energy required for promoting 5p electron. That means that in xenon, the energy provided from xenon to the excited xenon to travel these molecules to the d electron is lesser than the energy which actually forms the bonds of fluorine with them. So it already accommodates. ज्यादा एनर्जी मिल रही है फ्लोरीन के साथ एटम बनाने में देन इन इलेक्ट्रॉन्स को डी ऑर्बिटल्स तक फैलाने में, तो वो जो है कॉम्पनसेट कर देती है उस एनर्जी के लिए. तो इस तरह की इलेक्ट्रॉनिक स्टेट इज वेरी फिजिबल. फाइन. That means this kind of electronic state is more feasible because of the movement of these electrons to the d electrons. Right? Next slide. Now reaction with other reducing agents. What happens with the reducing agent? Because halogens are the oxidizing agents. Iodine is the weakest oxidizing agent among the halogens, as we all know, because halogens are the oxidizing agents. They actually tend to reduce themselves by taking up an electron. So all the halogens are oxidizing agent. Fine. However, the oxidizing agent or the activity of oxidizing decreases down the group. So iodine is the least or the weakest of the oxidizing agent. Fine. Next. So if we get to see that all halogens oxidize Fe2 to Fe3 plus. Ferric to ferrous is being oxidized. Who oxidizes them? Any of the halogen can. Right? So you get to see that all are oxidizing agent, but iodine does not have good enough oxidizing potential, you can say, to oxidize iron, that is ferrous to ferric to ferrous. Fine. You get to see here that chlorine, bromine and even fluorine can oxidize ferric to ferrous, but iron cannot. Iodine cannot. Right? Though it's an oxidizing agent, but the oxidation, the standard electrode potential lies above that of the iodine. You must have studied in your electrochemistry. You have studied your electrochemistry. You get to see the feasibility of the reaction comes up if E naught is positive. Fine. Delta G should be negative for a spontaneous reaction and delta E, because delta G is equal to minus NF E naught. So E naught should be positive, other way around. Fine. So E naught should be positive means if both the reactions are this way, this is not possible. If this is to be reduced, this is to be oxidized, the reaction is to be inverted. Inverting this reaction will vary the sign. It will become minus. If I add these two, the magnitude will be negative. That means E naught will be negative. So this is not a spontaneous, or you can say a feasible reaction. Fine. So iodine won't oxidize ferric to ferrous. Although if I invert this, this will be minus. If I add these two, plus 1.07 and minus 0.077, will in turn get me any E naught value as positive, and so for the above, any of them. So these reactions are feasible. However, iodine cannot oxidize ferric to ferrous. This may be asked in your JEE exams as an MCQ. Fine. Next slide, please. All halogens except iodine oxidize S2O3 to SO4 minus sulfate. Fine. Thiosulfate to sulfate. Chlorine, fluorine, bromine. All of them bring out this kind of an oxidation. But iodine does not. And this application is being used for the iodometric titration because thiosulfate is not reduced to sulfate ions. Rather, they are reduced to some other form which imparts color. And then we can get an iodometric titration. This is the application of an iodometric titration, that it's only iodine which, being an oxidizing agent, cannot oxidize thiosulfate. That is why thiosulfate to sulfate, that is why it is being used in iodometric titrations. Fine. Next slide, please. Now, displacement reactions. You all know that displacement reactions in normal terms get to say that if there are two places or vacant seats putting up, already two people are sitting over there. Now, they can be displaced only when a stronger person comes in or more reactive person comes in. Then only the less reactive will actually accommodate the stronger and will get displaced by the stronger one. So this is the whole concept of displacement reaction. As we know that moving down the group, the reactivity decreases. Fluorine is most reactive, thereafter chlorine, then bromine and iodine. So the more reactive will displace the less reactive ones. That's the whole concept of the displacement reaction. That means if you get to see that chlorine is sitting idle, however, bromine is sitting as ion. It could be NaBr, it could be KBr, any of the molecule, fine. So chlorine will come and make a reaction visible with the ion form, and bromine will come up as bromine molecule. You can say the more reactive will displace the less reactive in the reaction. Fine. So the displacement reaction goes like this. That means all the halogens, iodine, bromine, chlorine, all of them can be displaced by fluorine because that's the most reactive. Chlorine can displace bromine and iodine. However, chlorine cannot displace fluorine because fluorine is itself more reactive than chlorine. Fine. So is the case with bromine. It can displace iodine, but it won't displace chlorine and fluorine. Fine. And iodine cannot displace anything. Clear? Next slide, please. Here is the reaction summary of all. Because fluorine won't displace fluorine, so there is no reaction. But no reaction will take place for chlorine, bromine and iodine also, because fluorine cannot be displaced by anything. It's the most reactive. Fine. However, with chlorine, fluorine will displace it, giving a pale yellow solution formed by the chlorine molecules. Chlorine gas being released will form a pale yellow solution. Fine. However, there won't be any reaction for rest of them because they are less reactive than you can say chlorine, so they won't displace them. Next slide. So is the case with bromine. Bromine will be replaced by fluorine, will be replaced by chlorine, but there won't be any reaction with iodine. And there won't be any, you can say with iodine, in the case of iodine, all of them can replace iodine except iodine itself. Fine. Next slide. Next slide, please. So here comes the question, that which of the pair of reactants will not result in displacement reaction? Bromine and sodium iodide. Sodium iodide will get displayed by bromine because bromine comes above that. Chlorine and sodium iodide. Again, iodine can be displaced by either of them. So again, it will get displaced. Fluorine and sodium chloride, because fluorine is above chlorine, so it will displace it. The only option left is iodine and sodium chloride. Iodine won't displace anything. Fine, so this is the option. But you need to be very sure while reading out a question whether it is asked the pair of reactant which will not result. Here I have marked not in orange, but in your question papers many a times what you make a mistake that you do not read the question clearly, whether it is asked for an opposite option or the other way around. Right? Most probably you will find that rest of the three options are coming up in accordance with the one. Fine, but that three options will be displacing, won't be displacing, and one won't be. But it won't be true always. So please read the questions very carefully. Next slide. Now, disproportionate reaction. Proportionation reaction is a chemical change where the oxidation and reduction happens at the same species. Though in redox reactions, what happens? That the oxidation and reduction happens simultaneously, but on the other species at the expense of each other. Fine. A oxidizes to A plus, but B minus reduces to B. This is what happens. However, in disproportionation reaction, the same species gets oxidized and reduced at the same time. Right? How? We can see. Next slide. Here is a reaction. This is a very peculiar reaction, very frequently asked in JEE exams. I guess last year also there was a question in 2015 that chlorine water, what happens to the chlorine water on standing? Now you can see that water, reaction with water and chlorine, you must have come across that many a times the MCD water or Delhi Jal Board water is being treated with chlorine. Many a times the advertisement comes up in Doordarshan and they say that put a chlorine tablet in a water of a 1 liter or a 1,000-liter jar, and that will actually clear the impurities or any kind of a bacteria and all that. So what happens and how it actually goes on? Now look at the reaction. Chlorine with water forms HCl and HOCl. HOCl is chloric acid. One is marked for. Fine. Chloric acid is being formed along with HCl. How? The chlorine water gives you HCl and chloric acid. Next slide. So the chlorate ion, that is the chloric acid, HOCl, is known as the hypochlorite ion. This is a very unstable. Although in the presence of sunlight, or you can say when the temperature is increased, it actually decomposes to form HCl and oxygen. It gives oxygen back again. Fine. But next slide, please. What happens when there are already impurities putting up? There is a closed jar where no sunlight, no increase in temperature is provided. What happens to the dyes or kind of impurities? You get to see many a times you put a chlorine tablet to a colored or a dirty water. When you filter it up, because the impurities will settle down at the bottom, when you filter it up, you get a clear water. How it happens? Because you can say when chlorine and water was actually reacting, they form HCl and HOCl. However, HCl remained there only, but HOCl combined with the colored dye, or you can say the impurity which is imparting color to the water, and then it oxidizes the dye, because you know chlorine is an oxidizing agent, right? So it oxidizes the dye, and addition of oxygen in the dye happens and the color oxidizes. As the color oxidizes, the color flows off, right? It goes off. So is the impurity, and chlorine in the form of HCl remains behind. Fine. So if a question is asked that what happens to a chlorinated water while being like whose color changes, what remains behind? So obviously, if you need to be very cautious while reading out the question, whether the question demands what is it is demanding upon, whether it is demanding upon it is a chlorine water, what it gives. Chlorine water will give HOCl and HCl. But if it says that on standing or under the sunlight, what it gives, because previous slide please, because we have already seen, previous slide please, we have seen that it's very unstable. HOCl is very unstable. So under sunlight or high temperature, it reaches out to give HCl. Fine. So in that condition, you should write only HCl. Fine. And if the question is asked that chlorine water in presence of a dye or a colored chemical which actually diminishes the color, what should be left behind? Next slide. Again, it will give you only HCl. Previous slide, please. Once only. Yeah. HCl. Because HOCl will oxidize the dye to convert to HCl. So you have to be very clear that what they are asking, at which stage they are asking that chlorine water is producing what. If it is a simple chlorine water, it is going to give you HCl and HOCl combination. If it is kept on standing under a sunlight or increased temperature, it will only give you HCl, because HOCl will decompose or will get unstable. HOCl will transform to HCl. If there is a dye or an impurity which has been actually settled to a color, has been actually diminished because of the chlorine water, again there will be HCl only, because HOCl has oxidized the dye and have in turn converted to HCl. Right? So you need to understand at what stage they are asking the formations of the chlorine water. Clear? Next slide, please. Now reaction with water. Because chlorine water question was already there in the last year JEE exam, so I just discussed in brief. Reaction with water for bromine is also the same way, but obviously the reactivity goes on decreasing as we go down the group. Though it actually acts just same as chlorine. It forms HBr and HOBr, but to a lesser extent, because only slightly soluble in water. Not that greatly as chlorine is, because the reactivity is decreasing down the group. So mainly exist as molecules in saturated bromine water. So reaction with water on hydrolysis takes place, and you can see here HBr and HOBr, same as in the case of chlorine, is being formed. Next slide. And similarly here also, HOBr is unstable and it can bleach a dye or any of the impurity the similar way chlorine does. Fine. But we do not use bromine tablets. Rather, we are more prone to use chlorine tablets, because bromine is less soluble. The solubility is less. So the cleaning effect is also less in comparison to the chlorine. Chlorine is more efficient. Fine. Next slide, please. However, iodine does not react with water. It's slightly soluble. So iodine won't create any kind of a cleaning, or you can say imparting any oxidation to the impurity or the dye. So that kind of property is not governed by iodine. So we do not use any iodine, you can say iodine capsules for cleaning water. Next. However, fluorine. What about the fluorine, the most reactive one? It reacts vigorously with water to form hydrogen fluoride and oxygen. Now here is a very different story. It's not at all like forming HCl and HOCl or HBr and HOBr in case of chlorine and bromine. What happens here is, it is rather forming HF and oxygen. It is behaving differently with water as in case of chlorine and bromine, though iodine is not at all reacting with water. Fine. It is so reactive that, being so strong oxidizing agent, fluorine undergoes reduction rather than the disproportionation with water. It itself undergoes reduction, because I told you that it is the strong oxidizing agent. So it will perform a kind of an oxidation to the highest oxidation level. Right? So because of which it won't form HOF. Okay? It won't form HOF, rather oxygen will be formed. The highest oxidation state will be achieved. Fine. So this proportionation with water won't happen here. Fine. Next slide, please. You get to see here that reaction with water, chlorine reacts similarly at high temperatures. High temperature, I told you, or exposed to light, because HOCl is not stable, fine, under sunlight or high temperature. It decomposes to HCl. So in turn, you get this kind of a reaction. Pure HCl is being formed. So you need to understand that chlorine water decomposes to what? You understand the three stages. If it is only a reaction, what chlorine water consisting of, then it contains HCl and HOCl. So is with the bromine, right? But if it is kept under the sunlight or it under the elevated temperatures, the temperature has been raised, then it is going to give you HCl, because the HOCl in turn produced will convert to HCl. So it will be only HCl, right? And in the third case, if we say there was a dye which was imparting color, now there is no color. That means the color impartation must have been taken care well with the HOCl, and that has been already converted to HCl. So now my chlorine water will contain only HCl. Clear? Next slide. anomalous behavior of hydrogen fluoride. Now, hydrogen fluoride has a very anomalous behavior than the rest of the HCl, HBr and HI. How it is so? Because it has the highest boiling point and the melting point is also highest among the group. Fine. However, the trend was different for the, you can say, halogens. But hydrogen fluoride has the highest of the all boiling points. Next slide, please. Now, this is because of the bonding, the hydrogen bonding taking place between them. Why? Because so if I need to boil such an, you can say, compound which is actually having a branch chain kind of a structure where the weak bonding is happening, the hydrogen bonding is taking place. That means I need to actually break these bonds. Breaking these bonds will require more of energy, more of temperature will be required to bring about the boiling point, right? So there is a different, or you can say an anomalous behavior for hydrogen fluoride only because the hydrogen bonding takes place. Why hydrogen bonding takes place for the fluorine only, not with chlorine, bromine or iodine? Because fluorine has a almost the same size that of the hydrogen. So the bonding, or you can say the mixing, or you can say the friendship among them is very well as compared to the chlorine, bromine and iodine. The size becomes larger in comparison to the hydrogen. Fine. So the more the better the bonding, the hydrogen bonding. If I need to have a boiling point, I need to break these bonds as well. In breaking these bonds, I need require more energy, or you can say the more temperature. More temperature means higher boiling point. The boiling point will shift to the higher value. Only for the HF. Next slide, please. Now, acidic properties of hydrogen fluoride. Now you know that hydrogen and fluorine form very good bond. And there are hydrogen bonding among the intermolecular forces also. Like intermolecular hydrogen fluoride, there is a hydrogen bonding. One HF forms a hydrogen bond with other HF. So there is a good, you can say, bonding among them. Acidic strength means, what is an acid? What does acid means? Something which deprotonates or gives up an hydrogen is a good acid. The more the tendency of giving up an hydrogen, the more better acid it is. Fine. If hydrogen fluoride is forming a very good bond with hydrogen, the fluorine is finding very good bonding with hydrogen. It won't give up hydrogen very easily. That means the acidic strength will be the least. It will be the least acidic. Being acidic means it should give away hydrogen. Fine. And as we go down the group, the bigger size iodine will have least bonding with the hydrogen. So it will have the greatest tendency to give away the hydrogen very well. In that case, HI is the having the greatest acidic strength. And the other way around, this time, the acidic strength increases down the group. Fine. Because it is about giving away the hydrogen. Since HF is very well bonded with hydrogen all the time, it won't allow hydrogen to go away and give an acidic kind of a nature. However, iodine not getting very well because of its very big sizes compared to the hydrogen, they do not bond very well. So because of which it gives away hydrogen very easily, or you can say very at great good condition. So in that very case, it is having a good acidic, or you can say it's a good acid. Here you can see the acid dissociation constants are of great difference also. Fine. So that means the degree of dissociation is so less for HF and so high for HI. Fine. So the acid strength increases down the group. Something increases down the group rather. Next slide. That is the acid strength. Now this is the lab preparation of halogens. This is how the halogen can be prepared. However, fluorine cannot be prepared this way. This preparation comes up for all the halogens except for fluorine. Fine. So what happens in this? You can see here in this chamber where we start up is. Here we are performing preparation for a chlorine. So we have taken NaCl. If we need to prepare bromine, we need to take NaBr. If we need to take iodine or prepare iodine, we need to take NaI or any of the alkali halide. Whichever halide halogen I want to prepare, that alkali halide I need to take. Fine. Along with MnO2. If I heat providing H2SO4 to the same, what will happen? some gas will pass through here and will settle up in water. And then I let it allow to move through concentrated sulfuric acid, and which allows the chlorine. Now this is very easy to see and understand, but what are the chemical reactions undergoing this kind of a lab apparatus? Let's see. Now, when NaCl MnO2 was taken in this chamber and HCl was allowed to actually pass in this very chamber, what happened? Na2SO4 and MnSO4 formed, right? Along with H2O and chlorine. As this whole of these, you can see then water and chlorine, all these were actually made to move to the next chamber. And to remove HCl, water was used, fine. And from here, it was allowed to move to the chamber consisting of concentrated sulfuric acid. And then, free from HCl and water, chlorine was trapped. What happens if I do not take up MnO2? If I would not have taken MnO2, what would have happened? My reaction would have given me NaCl and H2SO4. NaCl and H2SO4 from here. Then I would have got HCl and NaHSO4. I would not have got Cl2. I would have got an acid. So how an HCl can be prepared? I can react my of the, you can say, alkali halide, that is chloride in the form of chloride, should be reacted with H2SO4 and HCl will be formed. Fine? Next slide. Now, interhalogen compounds. Interhalogen compounds are the compounds formed with the different halogens. These are the compounds containing two or more halogens. There are different halogens combining covalently, because you know halogens are having 5 electrons in their outermost octet, so they cannot form the ionic bond with another halogen. For ionic bond formation, they need any of the metals. That means alkali metals, alkali earth metals, or anything, fine. But if they are forming interhalogen compounds, that means they are reacting with some other halogen compounds. There is going to be a sharing kind of a bonding, and that means a covalent bond is going to come. So that's why these are the covalent compounds. Clear? Okay. Now these are generally more reactive than the component halogens. If we say the reactivity is the maximum, if we have a kind of a question where chlorine, fluorine, bromine, and some interhalogen compound is also mentioned, which is the most reactive. So we should always mark that it is the interhalogen which is more reactive even than the fluorine. Why it is so? Because they are actually having the weak covalent bond among them. Being reactive means ready to react. They never react in the molecular state. They always react in the ionic form. When the covalent bond is weakest in them, what happens? It readily dissociates and actually reacts very well. So the interhalogen compounds are more reactive than the component halogens even, fine, due to the weakness of covalent bond between dissimilar halogen atoms. So you get to see different interhalogen compounds. Let's come up with the diagram, or you can say the structure of interhalogen compounds. Since these are in your course, if we get to see the interhalogen compounds, ClF3. If I draw a structure for ClF3, now there is chlorine with 7 electrons in its outermost orbit, or valency is 7. In that very case, 3 fluorine molecules should be accommodating here. 1 electron for all of them from chlorine and 1 from fluorine is forming a covalent bond. Now chlorine is having 7 electrons in total. 3 are accommodating with the bond pair of fluorine. How many are left? 4. 4 in turn will form 2 lone pairs. This is for ClF3. A T kind of a shape. T shape or T structure for ClF3. Fine. The next example we have IF5. So the main halogen is iodine. Again, the valency goes 7. 5 goes for the fluorine. Now it is left with one more fluorine, one towards you above the blackboard. The fluorine is here, that means, and there remains 2 electrons which will be taken up as one lone pair, which will be behind the blackboard, whiteboard. Fine. Now what kind of geometry it has? As I told you, this is a T-shaped geometry. What this geometry will be? This is in the same plane. The 4 fluorines are in the same plane. One is above the whiteboard, and lone pair are putting up at the back side of the whiteboard. What kind of geometry should be this? Make sure one thing, that when we mark for the geometry, we only look for the bond pair. Lone pair never ever involves for the geometry. Fine. So that means 4 of these in the plane and 1 coming outside. It will be square pyramidal. Lone pair will never be taken up in geometry because lone pair cannot be seen. It's not an atom. It's free electrons, a pair of free electrons. So it never ever takes up for the geometry formation. So it will be a square and a pyramid coming for the outside fluorine. Fine. It will be a square pyramidal. Fine. And the next one is IF7. IF7. Iodine is already there. 7 fluorine atoms. 7 fluorine atoms means I can form a kind of a pentagon over here. But it accommodates only 5 in the plane. 1 fluorine towards the whiteboard, from towards your side, and 1 inside. Clear? What kind of this geometry would be? Pentagon bipyramidal. It's a pentagon in plane, 1 pyramid coming towards you guys from the white blackboard, and 1 going at the back. So it will be pentagonal bipyramidal. Two pyramids